Welcome back, students. Today we are starting the second lesson, the lesson on electric potential and capacitance. But before we delve deeply into the lesson, I want to talk about potential energy. This is something that you came across in the 11th standard in the lesson on work, power and energy, which I did not take for you. So I just want to talk about that a little before we get deep into this lesson, because ultimately you will be talking about potential energy here. See, we know that when a force acts on a body, it is resulting in an acceleration. Now, what is acceleration? Acceleration is the rate of change of velocity, and velocity can change in one of the two ways, or both actually. Okay, one is the one way the velocity can change is this: the speed can change. Okay? The direction can remain the same, the speed can change, and as the speed changes, we say that the velocity changes. For example, if I drop something from a height, there's a force, the gravitational force acts on it, and its speed changes as it falls down. The direction does not change, you can see that, but the speed changes. So we say that there is acceleration of this body. And why is there acceleration? Because there is a force acting on it, which is the gravitational force in this case. The other type of acceleration is this: the speed can remain the same, but then the direction can change. And this happens in the case of the moon orbiting the earth, or the earth orbiting the sun. In both cases, the speed doesn't change much, but then the direction changes. It's like if a particle which is going with a constant speed, when it circles around another object, then we say that there is the change in velocity throughout, and it's caused by the centripetal force. We say that. So the short point is this: when a force acts on a body, it can change the velocity of the body in one of the two ways, or even both. Okay, the one way is to change the speed, and the other way is to change the direction of the body, or it can change both. Okay, so if the force acts in the same direction as the direction of motion, then it will change the speed of the body. If the force acts in a direction perpendicular to the direction of motion, then it will change the direction of the body. Okay. See, when the force acts in the direction of motion, then it changes the speed, is what we said. This is what we mean by work done. See, when force acts on a body, two things can happen: either the speed changes or the velocity changes. Whenever the speed changes, then we say that there is work done on the body. It can be positive work or it can be negative work. When positive work is done, the speed increases. When negative work is done, the speed decreases. When I throw a stone up, as it goes up, the speed decreases, which means that the force is acting in the direction opposite to the direction of motion. When it is acting in the same line, but then it is acting in the direction opposite to the direction of motion. So it has a braking effect on it. It is reducing the speed. So you say that the work done there is negative. The work done by gravity is negative. And when it comes down, when I drop the stone, then the body is moving in the direction of motion. So the speed increases now. You see, now the gravitational force is accelerating it. Now you say that positive work is done on the body. And you know that when force acts on it in the same direction as motion, then there is a speed change that is taking place. And since the speed change is taking place, you say that there is a change in kinetic energy. And you call this as a work kinetic energy theorem. We find that the work done, force into distance, is equal to the change in kinetic energy of the body. So the thing that you need to remember is that when a force is acting on a body in the direction of motion, then it is going to change the kinetic energy of the body. You see, the same thing will not happen for a force which is acting in a perpendicular direction. The body may be moving in this direction, but if the force is acting in a perpendicular direction, then the speed doesn't change. Only the direction changes, right? The direction of motion changes. So in that case, there is no change in the kinetic energy, because kinetic energy is half mv squared. Since the speed does not change, there is no change in the kinetic energy of the body. So when a force acts in a direction which is perpendicular to the direction of motion, there is no change in the kinetic energy of the body. But when a force acts in the direction of motion, either in the same direction or in the opposite direction, then there will be a change in the kinetic energy of the body. When the force is acting in the same direction as the direction of motion, it is going to accelerate the body. So positive work will be done, meaning that the kinetic energy increases. So when positive work is done, kinetic energy of the body increases. When negative work is done, the kinetic energy of the body decreases. I want you to keep this in mind. See, this is another view of what you already know. You know that when a force acts on a body in the same direction as motion, then the kinetic energy of the body changes. The speed changes. That you know already. When the speed changes, obviously the kinetic energy should change, right? Because kinetic energy is what? It is simply half mv squared. And you know that v changes here. Since v changes, half mv squared will also change, right? So whether you throw the body up or the body comes down, in both cases the speed changes. But when you throw the body up, the speed reduces. So the kinetic energy will decrease because you start with a certain speed and then the speed is reducing progressively. So the kinetic energy will also be reducing because kinetic energy is simply half mv squared. But then when the body falls down, then the speed increases. If the speed increases, half mv squared also will increase. Then the kinetic energy increases. So it's the same thing that you already know. As force increases, there will be acceleration. If there is acceleration, then there could be a change in speed. Whenever you see a change in speed, you say that the kinetic energy is changing. So the change in kinetic energy will have to be equal to the work done, F into T. Okay, so this is what you studied in your 11th standard, so which is the same thing that we would do here. The example that I have taken so far is the gravitational force. We will do the same thing with the electric force. So we know that when there are two charges, there will be an electrostatic force of attraction or repulsion. And based on that force, there will be an acceleration for that body. As the acceleration takes place, the speed can also change, right? If the force is acting in the same direction as the direction of motion of the body. if there is this change in speed, then the kinetic energy will also change. So the work kinetic energy theorem will be applicable for all forces, including the electrostatic force. Okay, so with this introduction, we will start talking about the electrostatic potential. To continue with the discussion that we have just had, I'm going to talk about the work kinetic energy theorem. Okay, to do that, we will consider a uniform acceleration. Okay, so this is not needed from the perspective of your 12th standard. You don't have to memorize this derivation or take it very seriously, but it's important because without this you may find it difficult to understand the rest of the discussions that follow. Okay, so I'm going to derive the work kinetic energy theorem, but keep in mind that this is not needed for your 12th standard. This is from your 11th standard. So we'll talk about this first so that you can understand further discussions. Okay. So we know when there is uniform acceleration, there are three formulas that are going to be used, right? And one of them is this formula. This is v squared minus u squared is equal to 2a and then s. So this is the formula, right? Let us suppose that I'm going to do some manipulation here. Let us suppose that I'm going to multiply mass with this. Okay, so this is the acceleration of the body. A is the acceleration of the body, and s is the distance it has covered, and then v is the final velocity of the body, and then u is the initial velocity of the body. And the body will have a mass, right? So I'm going to take the mass and multiply this equation with that. So I'm going to have m v squared minus m u squared is equal to 2 into m a s. Okay, and we bring the 2 to the other side, then I'm going to have half m v squared minus half m u squared equaling m a s. Okay, but what does this m mean? M a is a force acting on the body, and then s is the distance it has traveled with that force. So this is going to give you F into s. Okay, the force is acting in the direction of A clearly, and s will also be in the direction of A. Right? So you have this half mv squared minus half mu squared is equal to F into s. So this quantity I'm going to call as kinetic energy. So this is the final kinetic energy and this is the initial kinetic energy. So there is a change in kinetic energy. So I will call this as kinetic energy final and then minus kinetic energy initial, okay, which is equal to F into s. So this can be written as change delta in kinetic energy is equal to F into s. Okay. This is a simple derivation, but it tells you that the change in kinetic energy is equal to this quantity F into s. This quantity F into s is what we are going to call as work done. Okay. So work done is equal to change in kinetic energy. So what it means is that when a force acts on a body, it's going to change the kinetic energy if it acts in the same direction as the direction of motion. And that change in kinetic energy will be equal to this quantity F into s. And that quantity is what I'm going to call as work done. Okay? So in this case, the body is moving in the direction of acceleration. Let us suppose that the body is moving in this direction, let's say. This is the direction in which the body is moving. Okay? Now, the force may be acting, so this is a body. The force may be acting in this direction. So there could be an angle between them. So this is the direction of force and this is the direction of motion. Okay, let's suppose that. So what did we say? We said that only the force which is acting in the direction of motion will change the kinetic energy. Right? Because say drop, the force is acting in the same direction as the direction of motion, so the speed changes, the kinetic energy changes. The force which is acting perpendicular to the direction of motion will not change the kinetic energy. Okay? So, in this case, the force is acting at an angle theta to the direction of motion. Then how do I approach this? What I can do is I can resolve this force into the horizontal component and also the vertical component. And which component will change the kinetic energy? This component will change the kinetic energy. Because that is a component which is acting in the direction of motion. So that will change the kinetic energy. And that will change the speed. Okay? So I take this force and I can resolve it into two parts. So one is, right? So this is F horizontal and this would be F vertical. So direction of motion. Okay. So now work done. What is work done? Work done, you write work done, ability is equal. This is equal to force in the distance, but which force? I can't take the entire force, right? Because the entire force is not going to change the kinetic energy. Only the component which is in the direction of motion is going to change the kinetic energy. So Fh into whatever distance it travels with the force, okay, into that S. Or I can say it's D. Okay? But what is Fh? This Fh is actually F cos theta. F cos theta into D. I rearrange this, then I have F D cos theta. So that should ring a bell. F D cos theta, it looks more like a dot product, a vector dot product, right? So I can say that this can be, this F D cos theta can be written as F vector dot D vector. V and D is the vector, right? So D vector. So F dot D is the work done. So when work is done by a force on a body, its kinetic energy will change. That's the whole idea. A force can act on a body and not change the kinetic energy. In that case, the force must be acting perpendicular to the direction of motion. When a force acts on a body and changes the kinetic energy, the force must be acting in the direction of motion, or opposite. And when a force acts on a body at an angle to the direction of motion, it's going to have both now. It's going to have a horizontal component and also have a vertical component. And this horizontal component will change the speed. And this vertical component will change the direction. Okay? But then when you calculate the work done, you would be concerned only about this component that changes the speed of the body. Because only when speed changes, the kinetic energy can change. So, work kinetic energy theorem is a very important theorem in physics. And I want you to understand that well. If you do not understand this part of the video, go through it to understand what I am trying to communicate to you. And if you have any questions, get back to me. Without this, proceeding further could be a little difficult. Yeah, you may still do something, but you won't understand what's going on. Okay? But understanding is key. Hope this is clear to you. the work kinetic energy theorem, and we also know now that what work done is. Let's see if you can understand what I'm going to do now. Okay? Let me take this book. The book is here. What's the kinetic energy of the book right now? It is 0, because it does not have any speed. Okay? Now I'm going to move it up this way. So what's the kinetic energy of it now? It's again 0. But you can see that I applied a force to take it there. Okay? So it's here, the kinetic energy is 0, and when I take it up, the kinetic energy is 0 again. But what did we just say? We said that when a force acts on a body, it is supposed to change the kinetic energy. Okay? Particularly when the force is acting in the same direction as the direction of motion. Right? So the body moved like this. So I applied force like this. So there was a motion in the direction of force. But then the kinetic energy has not changed. I started with 0 kinetic energy, and then I end with 0 kinetic energy. Then what has happened here? How can I explain this? So the book was here. Kinetic energy initial was 0, and then I took it up. Okay, my force, I'll say force of Swaminathan, okay, and say this force of Swaminathan was acting on it, and then I took it to this place. And here it's initial kinetic energy, and here also the kinetic energy final was 0. You see, the body moved in this direction, there was force applied in this direction, which means the kinetic energy must have changed. From 0, this must have become something else. But why did it remain 0? That's the question. To understand it, you need to observe it a little more closely. Yes, my force was acting this way. But my force is not the only force acting. Well, all in all, force of gravity was acting on it. Okay? This force of gravity was acting on it. So when I took it from here to there, that force was also acting on it. The displacement was in this direction, and gravitational force was downward. So what was it trying to do? It was trying to retard the motion. This body was trying to go up, and gravity was trying to pull it down. It was having a braking effect. So it was doing negative work. It was slowing it down. Okay? So the work done by gravity, when I move the body from here to here, so this is point A to point B, let's say there is a height of h. Okay? So I took the body from A to B in this direction, and gravity was acting down. So the work done by gravity is what? Let's think about it. So work done by gravity, because there are two forces, right? Each force will do work. Work done by gravity, Wg, is equal to force of gravity into this displacement d. Okay. D is in this direction. So I'll say h. Okay. In this case, h vector. Okay. H is in this direction. That's the direction of displacement. Displaced from here to there. Okay. F dot h. So what is that? It's going to be f g h cos theta. What am I going to get now? Fg is mg, and then h is the height it's going it traveled, the distance it covered. But what is theta? You see, Fg was down, and then H was here, right? Up. Displacement was up, Fg was down. So the angle between those two are 180 degrees. So then cos 180 is -1. So I can say that gravity did negative work. Gravity was trying to slow it down. That's the meaning. I mean, finally, I'm trying to make my math match with reality. We can see it clearly. Okay, when I was trying to take something up, then the gravity was acting down. The gravity was not absent there, right? Gravity was there. So there was displacement here. So gravity was there. So how do we define work done by gravity? Force into displacement. Okay. So then when we do that, clearly it was trying to slow it down. Okay. So you get a negative work. But then what was it trying to do? Work done by me. I was trying to accelerate it up. Right? I was trying to accelerate it. I was trying to speed up because it was at rest. Then it had some speed. Right? Without speed it couldn't have moved there. So it had some speed and then it stopped here. So the work done by me, Ws is equal to force of Swami to same h. So I also did work. My force did work on the body. Gravity also did work on the body. So this is what I get here. But I have no idea how my force acted. I don't have an equation for my force. Was it constant like mg? I don't know. Maybe it wasn't. Was it varying all the time? And if it was varying, how much was it varying? How was it varying? I have no idea how my force can be represented through an equation. I don't have an equation for my force. All I know is that I applied force. That can be nothing now. Okay, maybe like it's equal to mg now because it's not moving. Then it might be slightly more than mg, right? And then it kind of stopped there. So then I even might have even I myself may have prevented it from accelerating further. So my force may have acted downwards too. But the simple point is this: I have no idea how my force acted. I don't have a single direction. I may not have a single direction for my force. I may not have a single magnitude for my force. My force may have been a varying force. I have no idea. Okay, but what do we know? All I know is that this is going to be F Swami and then H and then cos 0, right? Because Fs was acting in this direction, this, and then H was also in this direction. So the angle between Fs and H is 0. So this cos 0 is 1. So notice here it is Fsh. Okay. So assuming that my Fs was constant, okay, let's assume that. Then I'll have this. Otherwise, like I'll have a different expression there. But let's not worry about it. But this is positive work I do. I've done positive work, but gravity has done negative work. So what has happened is that I changed its kinetic energy. Gravity also changed its kinetic energy in the opposite direction. So the net change is 0. So I can say that, if I do this, work done by gravity must have resulted in change in kinetic energy due to gravity. Okay? And then work done by me is equal to change in kinetic energy due to Swami. So what's the net change? This change plus this change. But that is 0. Right? So net change in kinetic energy must be equal the change due to gravity plus the change due to Swami. Okay? Then what does it mean? It means the delta, and this is also equal to 0, right? Because we know that there is no change in net change. It had kinetic energy of 0 in the beginning, and it also had a kinetic energy of 0 in the end. So the net change is 0. So I can say that delta KEG is equal to minus delta KES. Or KES is equal to minus delta KEG. Okay? Or I can say that delta KES is equal to minus delta KEG. Okay? So the work I did was opposite to the work done by gravity. So what's the work done by gravity? It's minus mgh. Okay? So minus of minus mgh. So I have done mgh. If gravity did negative work, then I did positive work. And I did the work to the same amount as gravity did. But I did positive work. Gravity did negative work. So when you put them together, there is no net kinetic energy. So there is no net work done in the body. Because there is no net work done, there was no change in kinetic energy too. Individually there was. If I take just my force alone, there was work done. I had a positive number. Then that must be a positive work done. But at the same time, my force was not the only force which was acting on the body. Gravity was also acting on it. So as the body moved, gravity also did work, but it did negative work. And that work and my work were equal. And that is why there was no net change in kinetic energy. Okay? I want you to understand this. This is very critical. Why you'll get to know pretty soon. But understanding this is key. When a force acts on it, let's say the body is moving this way. You don't know that there could be 1,000 forces acting on it. Body being moving this way. Okay, there could be 1,000 forces acting on it. But if the kinetic energy does not change, suppose it moves with some 10 meter per second speed, and then there are 1,000 forces acting on it, and it still continues with 10 meter per second speed, which means its speed has not changed. If the speed has not changed, it means that the net work done by all these forces must be 0. Some forces may do positive work, some forces may do negative work, but effectively, taken together, the net work done on this body is 0. And that is why the speed doesn't change. In other words, the kinetic energy does not change. Okay? So in this case too, there are two forces acting on this body. One is gravity anyway, and the other one is my force. But then I moved it. Even though I moved it, by applying a force, there was no change in kinetic energy from the initial and final positions. Which means the work done by gravity must be equal to the work done by me. Okay? So, I may not know the force. I may not know the details of the force I apply. My force could be varying. But what I do know, by comparing the kinetic energy in the beginning and kinetic energy in the end, what I do know is that the work done by me is equal to the work done by gravity. Okay? If the work done by gravity is minus mgh, because it was acting in the opposite direction, negative work was done, gravity was trying to slow it down, this was trying to move up. So if the work done by gravity is minus mgh, the work done by me must be mgh. So even though I don't know the nature of the force I have applied, I know the work I have done. What's the work I have done? The work I have done must be plus mgh. So I can express the work I have done in terms of the work gravity has done. That's a great advantage. I don't know the details of my force. I don't know how many newtons I applied. I don't know whether the force was constant or varying. I have no idea. But what do I know? I know that the work done by me must be equal to the work done by gravity. Why? Because initial kinetic energy is the same as final kinetic energy. And I know that gravity was acting in the opposite direction. So the work done by gravity must be equal to the work done by me. So even though I don't know anything about the force I have applied, I know the work done by my force. The work done by my force is a negative of the work done by gravity. So gravity did negative work, the negative of negative would be positive. Of course, I did positive work. I moved the body in the direction. I applied the force in the direction of motion. I was trying to accelerate it. Understand? Okay. Hope this is clear to you. What we have done so far, we are now going to talk about potential energy. We talked about kinetic energy, and now let's see how the potential energy is defined. A potential energy is defined as the work done by an external force against the conservative force without any acceleration of a body. So it's like this. You have a body which is in a conservative field, and now you're going to do work against that field in moving that body, and you're going to do that without any acceleration. Okay. Why? It is this. Just as we discussed, okay, if I take this body, now this body is in the conservative field of gravity. Right? Gravity is a conservative field. Let us talk about what a conservative field is a little later, but let us, for the time being, let's just take it for granted that gravity is a conservative field. Okay? So there is this force acting on it. So this body is in a conservative field. Now, what is it doing? It's pulling it down. Basically, gravity is acting on this, and it is pulling the body down. But when I take it from here to another place, what am I doing? I am doing work by applying my force, the external force, against this conservative field. So I do it, I take this body from here to this place. So I am moving it against the conservative field. The conservative field is, it's attracting this, but I am moving it against it. So the work done by the external force against the conservative force. Okay. And I have done it without any acceleration. Why? Because the kinetic energy has not changed. It was 0 here and it is 0 here. So I started from here and then I stopped here. So there is no acceleration, if you think about it, between the initial and the final positions. Suppose there was an acceleration. So let's take a point somewhere here. I'm going to move this point, the body from here to this position. But let us see what is happening when it is moving here. You see, when it is moving here, it had some velocity. And when it started here, it didn't have any velocity, it didn't have any kinetic energy. But then when it was moving at this point, it had a velocity. It had kinetic energy, which means it had a speed which is different from 0. So there was an acceleration. Okay, I cannot consider that because now it is accelerated, right? During the process it was accelerated. But take initial and final positions now. Initial position, the kinetic energy is 0, and the final position, the kinetic energy is again 0. So the velocity, the speed remains the same. So there is no acceleration at all. Okay. So, and what is the work I have done? And that must be equal to the work gravity has done in the opposite direction, right? And that is why there is no change in kinetic energy, okay, of this body. So this is what we call as a potential energy. Notice it was here, then mg is a force, and then I move it here, then it's mgh. That was a work done by gravity, and the work done by gravity is minus mgh. We saw it, and the work I have done is negative of that work done. So minus mgh is the work I have done. by lifting it from here to this position. So mgh is the potential energy of this body. Why is it so? The moment I remove my force, then what happens now? And that this force starts attracting it from the position, then it's going to gain speed. So it will come back to the old position, but then it will have kinetic energy now. So it has got accelerated from this position to this position. Okay. So the potential energy now gets changed to kinetic energy. Okay. So again, let me repeat, the definition is this: the potential energy of a body in a conservative field is equal to the work done by an external force against the conservative force without acceleration. Okay. If I were to do it like this, let's see, I'm moving it like this, then what am I doing really? I'm doing work in the same direction as the gravitational force. So then that is not it. I can't say that is the that is equal to the potential energy. I need to do the work against the conservative force. Okay, so against the conservative force. But if I bring it down pretty fast without stopping, okay, then my force is acting in the same direction as the gravitational force. Then it is that is not potential energy. Okay. So for potential energy, you need to work against the conservative force. Okay, so that is very important. Let's define it like this: potential energy is equal to the work done by the external force against the conservative force without acceleration. Okay. Okay. So work done against, let's say, versus a conservative force. Okay, let's say force conservative without acceleration. Explained all the parts. So the work has to be done by an external force, not by the conservative force, and it must be against the conservative force. Okay. In the case of gravity, it's acting down, but then I need to take it up. The work done has to be against the conservative force too. And then, what's the third point? It must be without acceleration. I can't act. If I start at zero kinetic energy, I should stop at zero kinetic energy. Okay, so there should be no change in kinetic energy. So then that is what is called as the potential energy of the field. Okay, so if you understand this, then we are fully ready to go into this the lesson deeply. Okay? So all this has been an introduction for you. I have just refreshed the concepts that you must know before you get into this one. Okay. So whatever we have been taught in the 11th standard has been briefly touched in this lecture so far. Hope this is clear to you, and then we will get into the lesson now. The potential energy in an electric field. Okay, let me take a point charge. That will be Q1 here. Okay, so this is Q1, and I'm going to have another charge. This is positive. I take it as positive, and I'm going to have another positive charge. Okay, suppose that is at this distance. This is at this distance. This is Q2. This is also positive. So Q1 is positive, Q2 is also positive. And now that position is, let's say, R1. Okay, that is R1. And I want to move it from this position to another position, say R2 here, towards it. Why? Think about it. What is the conservative force going to do? There will be a force of repulsion. So the force acting on this will be in this direction. Force from the field. Okay. The electric force will be in this direction because it will try to push it in the direction. So what should I do? Then I should do work against that force, which means that I must be pushing it towards this charge. So I will go from this position, which I will call as A, to another position I will call as B. Yeah, I'm going to go this way. Okay. The direction of movement is here. And let's say that is going to be, that distance is going to be R2. So I'm going to move this charge Q2 from position A to position B against the conservative force. Okay? This force, the electrostatic force, is repelling. If we just leave it like that, it's going to go from here to someplace. I mean, to infinity, if you think about it. It'll keep going. But now, what I'm trying to do, I'm trying to bring it from this position to this position. So I'm moving it in this direction. You notice what I'm trying to do. What kind of work I'll be doing? I'll be doing positive work. Why? Because the direction of motion is this. And then I'm also going to apply the force in this direction. Because it is pushing this charge like that. So I want to apply the force in the opposite direction. So that is this direction. And I'll also be moving in this direction. I'm moving in this direction. So the force is applied in the direction of motion. So I will be doing positive work. But what is the work this force will be doing? This electrostatic force will be doing? This will be doing negative work, because you see, as the body is moving in this direction, the force will be trying to apply brakes on it, right? So it will try to push it in that direction. So the electrostatic force will do negative work and I will do positive work. Let's try to do it now. Let's try to do the mathematics of it. Okay. So what's the work done by me? I call it as Ws. Work done by Swan. Okay. And that must be equal to work done by the electrostatic force then negative of that. This will do negative work, WE will do negative work, but that WE is negative work. And negative of negative will give me positive. So I will do positive work and this will do negative work. So Ws, the work done by me, must be equal to negative of WE. Again, I don't know what kind of force I am going to apply. I don't know an equation for my force, the external force, but I can take the equation for the electrostatic force. I have an equation for it, right? F is equal to K, Q1, Q2 by R squared. That is the electrostatic force. I have an expression for that. I can make use of it. I can make use of it and find the work done by electrostatic force, and if I assign a negative sign to it, then I would get the work done by me, and that would be the potential energy. Okay. So we'll do it now. So what's the work done by the electrostatic force? Okay, the electrostatic force, work done by this is equal to K Q1 Q2 by R squared sometime and dr, okay, delta dr. Okay, so this is what you will get here. So this dr will be negative. Why? Because you are coming from a greater distance to a smaller distance, so this will be a negative number, all right. So anyway, you are going to have K, Q1, Q2 by R squared. Okay. So as this is your f, and this is your small distance dr. So integral this from r1 to r2. When you take this path r1 to r2, then dr will be negative because r1 is greater than r2. If you think about it, so any distance will be so you're coming from a greater distance to a smaller distance. So final is smaller than the initial, so dr will be a negative number, and kq1 q2 by r square would be positive. So the work done would be negative, and I am going to sum it all up here. Okay, so that is what I have here. Why? It's because work done is equal to f dw, small amount of work done is equal to f dot dr. Okay, so that is the expression. So this would be work done by the electric field is equal to kq1 q2 by r square into dr. You go from r1 to r2. So what do you get here? So I'll get minus k q1 q2 by r. If you integrate this, this is what you will get. And I would apply the limits of this. So this is r1 and r2. When I apply the limits, first I'll apply the upper limit r2, so that will give me minus k q1 q2 by r2, then minus of minus k q1 q2 by r1. Okay. So this should give me k q1 q2 by r1, because this will become plus, and minus k q1 q2 by r2. But what is this? This is actually the work done by the electric field. But what we need? We need the work done by the external field, or the work done by me, Ws. What should that be? That is negative of this. Negative of this. So then what external work, or Ws, that is also the external work, right? Then work done by external force. That must be equal to minus WE, electrostatic force. So the minus of minus, this will become plus and this will become minus. So I will get K Q1 Q2 by R2 minus K Q1 Q2 by R1. Okay. So this is a potential energy. So this is the potential energy. Okay. Couple of things you can see here. So what is the work done by the electrostatic field? KQ1, Q2 by R1. So what is R1? R1 is a bigger number. So that's the denominator. So this is a smaller quantity than KQ1, Q2 by R2. Okay, and this whole thing will be a bigger quantity. So you get this bigger quantity is a smaller quantity, because this R2 is smaller, but it is in the numerator. So that will make it bigger. R1 is bigger, but it's the numerator again, so it will make it smaller. So smaller minus bigger will give you a negative number. So work done by the external field is negative work. That is what we have been discussing, right? Because it is the electrostatic force is in this direction, when the body is moving in this direction, so the work done is negative. But here, work done by me is what? I am pushing it, applying force in this direction, body is also moving in this direction, so I am doing positive work. You see, when I do that, KQ1, Q2 by R2 is actually a smaller number, so this is bigger, and KQ1, Q2 by R1, that is smaller, so I get net positive number. So I get to do positive work. And electrostatic field gets to do negative work. But the work I do is equal to the negative of the work done by the electrostatic field. So I find the work done by the electrostatic field and assign a negative sign to that, then I get this stuff, the work done by me. So first I find WE and then I find WS. So that's the potential energy of the system. So now the system will have this kind of potential energy. And one more thing, whenever we talk about potential energy, we need to talk about potential energy of the system. It is never for one body. Okay, even though we talk of gravitational potential of, say, this chalk, okay, we ignore the earth. Okay, potential energy, unlike kinetic energy, potential energy is for the system, not for a body. Okay, kinetic energy is for a body, half mv square for this one, but potential energy is for the system. I mean, it is available for both. Even here, when you take this marker pen and then earth, the potential energy is available for both of them. But then, because of the huge mass of the earth, it will hardly share the potential energy. The mass is too heavy for the earth, I mean, it's too huge compared to this marker. So you ignore the potential energy of the part that has to go for the earth. You are ignoring it. You are assigning all the potential energy that you calculate only to this. Why? Because you see, before it reaches, it reaches the ground, that will hardly move. Earth will hardly, see, if we leave it like that, see, this is going to be attracted by the earth and the earth is going to be attracted by this. So both of them will try to reach each other. But then this will have a much greater acceleration than the earth. The earth's acceleration is so small. So it will hardly move. Even before it moves, this will go on greater. So I can say that even before the earth has any velocity, this would have touched it, gone and touched it. So I can say that almost all the potential energy is taken up by this one and leaves the earth with nothing. So there is absolutely a negligible amount of kinetic energy for the earth. But then all the kinetic energy is going to be had by this one. So this potential energy is for the system. Okay? And if I just leave them together, like suppose I have brought it here and if I leave it here, this will stop moving in that direction and that will stop moving in that direction. So the potential energy, when these two things are at this position, is going to be shared by this and this. So when you calculate the kinetic energy, you can't just take this kinetic energy alone. As I said, the potential energy is for the system. It's for both of them together. So when potential energy gets converted into kinetic energy, it's going to be shared by both of them. So this will have kinetic energy, this will also have kinetic energy. Understand it, right? So I have two positive charges here, holding them. There is potential energy here. You just leave them there, then what will happen? This will start moving in that direction, and this will start moving in this direction. Okay? So this will have kinetic energy, and that will also have kinetic energy. So this kinetic energy plus that kinetic energy will be equal to the potential energy. The only reason we ignore the kinetic energy of the earth is because the earth is too huge that it hardly accelerates before it goes into collapse. So almost all the potential energy is going to be taken up by this, and that's the only reason. Okay? But otherwise, potential energy is for the system, for the Q1, Q2 system, not for Q1, not for Q2. It is for both of them together. And when you leave them, both of them will go. This will have kinetic energy and that will also have kinetic energy. And this kinetic energy and that kinetic energy together will be equal to the potential energy of the system. So I want you to understand this. So the basic idea, let me reiterate, is this. What is potential energy? Potential energy between 2 points is this. Okay. Potential energy of a system is this. I'm going to take a charge Q2, I'm going to move it from A to B. As I move it from A to B, then I'm going to work against a conservative force. The amount of work I do against a conservative force is going to be equal to the potential energy of the system, and I have to do it without any acceleration. So that's the fundamental idea of potential energy, and the potential energy is for the system, the Q1 Q2 system, and it's going to be shared by all components of the system. In this case only two, Q1 and Q2, so it's like that. Okay, so now I have found we have found the expression for potential energy. Okay, so potential energy for the system Q1 and Q2. When I moved Q2 from point A to point B. Okay. Now we'll talk about potential. So potential is different from potential energy. We'll talk about that now. Keep this in mind, then we'll talk about it again.